Let me ask you something. What's the first thing you reach after getting a hot, crispy French fry? Salt, right? But did you know that tiny sprinkle of salt on your fries is actually made of something really amazing? That's salt, sodium chloride or NaCl.
Hello everyone, Aziza and me Anis will explain a little bit about the crystal structure of rock salt, more commonly known as sodium chloride, NaCl. While most people associate salt with food, its structure plays an important role in chemistry, material science and even biology. Rock salt is a classic example of an ionic compound and serves as a model for understanding how ions are arranged in a solid. Today, we'll explore its unit cell, atomic arrangement, coordination number and applications of the structure more clearly.
Well, table salt or NaCl isn't just a boring white powder. It actually has a super organized structure like a 3D puzzle. It forms what's called a face-centered cubic lattice, where each sodium and chloride ion fits into a perfect repeating pattern. But why? Why do they arrange themselves like that? It's because one of simple rule in chemistry, opposite attract. The positive sodium ions and negative chloride ions pull each other close and they settle into most stable, balanced shape possible. That shape, it's called the rock salt structure and it's one of the most famous examples of how invisible forces create something we see and eat every day.
So here is our model kits. So rock salt adopt a face-centered cubic, which is FCC structure. In this arrangement, the chlorine ion, which is the Cl, form the framework by occupy the corner and the face center of the cubes, and the another one, which is the smaller ion, which is the sodium, will fit into the octahedral hole within the lattice. So this symmetry will be repeating pattern to ensure the stable and tightly packed structure. So specifically the chlorine chloride located at the corner and the face of the center, while the sodium found at the edge, the center and the body center of this cube, as you can see here. By this arrangement, the perfect example of the ionic bond will be found, and it will be help to the electrostatic attraction between the opposite charge ion.
Now, let's calculate how many ions are present in a single unit cell. At the corners of the cube, we have 8 Cl- ions. But since each corner is shared by 8 neighboring unit cells, each contributes only 1/8 to the cell. That gives us 1 Cl- from corners. The 6 Cl- ions at the face centers are each shared between 2 cells, contributing 3 more. So, we have 4 Cl- ions in total. For Na+, there are 12 ions at the edge centers, each shared among 4 cells, giving a contribution of 3. Additionally, the Na+ ion at the body center is not shared and count as one whole ion. So, we have 4 Na+ ion in total. This results in a unit cell with 4 Na+ and 4 Cl- ions, conforming the 1:1 ratio to the empirical formula, which is NaCl.
Sodium chloride has an ionic bond. An ionic bond is a type of chemical bond that occurs through the electrostatic attraction between oppositely charged ions. This typically involves a metal atom, such as sodium, which loses one or more electrons to form a positively charged cation, and a non-metal atom, such as chlorine, which gains electrons to become a negatively charged anion. In this case of sodium chloride, NaCl, sodium donates one electron to chlorine. The resulting Na+ and Cl- ions are held together by strong ionic forces in a crystalline lattice structure.
So let's move on to the special position of this ion. So the chlorine ion found at the coordinate 0, 0, 0 and 0, half, half, which present at the corner and the face center of the cube, while the sodium ion, which is on the other hand, occupied the position like half, 0, 0 and on the edges, and half, half, half and the center of the cube. So this regulating spatial arrangement contribute to the higher symmetry of the rock salt.
One of the most important aspects of this structure is the coordination number. In NaCl, each Na plus ion is surrounded by 6 Cl minus ions and vice versa. The 6-6 coordination results in octahedral geometry where each ion is at the center of an imaginary octahedron formed by its neighboring ions. This kind of arrangement allows the crystal to be both mechanically stable and electrically neutral throughout.
So let's jump to the application of the sodium chloride. So we can see at the table, so it's a familiar use of the sodium chloride. So its usefulness goes for the beyond that. So the rock salt, it is widely used for the ice road in the winter because it's below freezing point of the water. In the biological, the sodium and the chloride ion are important for the electrolyte that help to maintain the osmotic balance and the muscle extraction. While in the industry, the sodium chloride is a key raw material that manufacture to the chlorine gas, the hydrochloric acid, and the sodium hydroxide of the important chemical in the modern world today.
To better visualize all of this, we created a 3D model using plasticine. In our model, the red balls represent chloride ions and the yellow balls represent sodium ions. The red balls from the face-centered cubic framework and the yellow balls fill the octahedral holes between them. This model helps demonstrate not just the shape of the unit cell, but also the repeating arrangements of ions and how their change alternate, leading to a stable crystalline structure.
So to conclude, the rock salt structure is elegant and the fundamental example of how the ionic compound is built. So with the face-centered cubic lattice, the coordination number is 6 and the simple 1:1 ratio. The sodium chloride is illustrate the many key principle of the solid state chemistry. So it is relevant to stretch from our dinner table and critical the rules of in the biological and the chemical manufacturing. So understanding of the crystal structure and of the sodium chloride, it is only depends on our operation of the chemical, but also highlight how the atomic level arrangement to determine the properties and use of the material around us. Thank you. Bye.
So next time you grab a handful of French fries and sprinkle a little salt on top, take a second to think. You're not just adding flavor, you're adding science. That teeny tiny salt grain is a beautiful crystal made from sodium and chloride ions, arranged perfectly in a structure we call rock salt, a face-centered cubic masterpiece formed by nothing more than the attraction of opposite charges. It's amazing how something so simple and so small plays such a big role, not just in chemistry, but in our everyday lives. So, whether you're in the lab or in the kitchen, remember, chemistry is everywhere, even in your fries. Thanks for listening and stay curious.